Since by now we've learned most of the basics like mean, standard deviation, and simple probability, we're at the point where we can begin to do statistical experiments. When we perform these experiments, there will be an unknown quantity we're studying. Our experiment could be flipping a coin, and we could be looking for the number of times that coin flip comes up heads. In a statistical experiment, the thing we're solving for is what's called a random variable.
A random variable is the unknown quantity we solve for in a statistical experiment, and is generally represented by the letter x.
We call x a random variable because its outcome is unknown before the experiment occurs, and its value will change each time we do the experiment.
If we're looking for the weight of the hoagie-eating boar, x equals the weight of the hoagie-eating boar. If we do an experiment and find the weight of the boar to be 112 pounds, then x would equal 112.
There are two types of random variables, qualitative and quantitative. Qualitative variables are variables that have more than one possible outcome, but whose outcomes can't be expressed using numbers.
It would be like asking people what kind of dessert they like. They may tell you ice cream, they may tell you fudge, but either way, you can't express their answers with numbers.
The other type of random variable is quantitative. Quantitative variables can be expressed using numbers. Think quantitative quantity. Quantity is a number.
With qualitative variables, the ones you can't express with numbers, once you've said the results, that's pretty much it. If you found someone's favorite dessert, there's not a whole lot there for you to analyze.
But with quantitative variables, the countable ones, we can calculate things like mean and standard deviation, which can keep frustrated college students busy for hours.
Because they have such greater potential for analysis and keep college students off the streets, quantitative variables are more widely used when conducting statistical experiments. Since that's the case for the rest of this video, when we say random variable, we mean quantitative random variable.
Now that we have that settled, let's look at the two types of quantitative random variables, discrete random variables and continuous random variables. The difference between the two types is fairly simple.
With discrete random variables, you can count the number of possible outcomes, and the results are integers. That means they're whole numbers, so decimals and fractions need not apply.
Discrete random variables are things like the number of errors found on a statistics student's quiz. Or, if that example makes you nervous, think about the number of tacos you've eaten this year.
Regardless of how those examples make you feel, each one has countable results. And that's why they're all discrete random variables.
On the other hand, continuous random variables can assume any number of possible outcomes. When we say any possible number, we mean any possible number. Think of a number line stretching to infinity. If you tried to mark every single number on the line, including decimals, you could never do it.
A good example of a continuous random variable would be something like picking a baby at random and trying to predict its exact weight before it's born.
The baby's weight is a continuous random variable because the weights of newborn babies have an infinite range of possibilities. With tenths of ounces to pounds, you'd need the powers of dozens of psychic friends to predict the outcome.
Does everybody got that? There's two types of random variables, discrete and continuous. Discrete, they're integers, they're countable. Continuous, they're integers, fractions, and decimals. They're infinite, and they're uncountable.
Each of these random variables has a different type of probability distribution. So first let's look at what a probability distribution is. Then we'll check out the specific types of distributions that go with our two variables, discrete and continuous.
Say we have a random variable like x. Whether x is discrete or continuous, a probability distribution lists all the possible values for x and the corresponding probability of those values occurring. Once we calculate these values, we organize them into a probability distribution.
But if we're using a continuous random variable, we'll use the distribution curve because there are too many possible values for x to use a histogram.
When we make our probability distribution, we need to define x. When we define x in a generic sense, we use big X. Like big X equals the number of trips to the dentist during my life. When we assign a specific value to x, we use little x. So we'd say little x equals 4. Little x will always be a number, big X will always be a name.
Let's look at an example of how to make a probability distribution for a discrete random variable. Remember, when we find probability, it'll always be somewhere between 0 and 1, and the sum of all the probabilities in the distribution must equal 1.
Meet Maternity Glenda. Maternity Glenda is pregnant, only she's carrying twins.
Let's see what the chances are of maternity Glenda giving birth to 2 baby girls.
Let's have big X represent the number of female babies maternity Glenda gives birth to. We then list little x, all the potential values for big X. In this case, big X, the number of female babies maternity Glenda gives birth to, can be 0, 1, or 2. So our potential values for little x are 0, 1, or 2.
All this big X, little x stuff is a confusing way of saying that X represents the number of female babies Glenda can have, and the potential values for X are 0, 1, and 2. How do we know what these potential values are? Well, assuming that maternity Glenda obeys the laws of nature, the babies will be either male or female. With male and female babies, there are 4 possible events for this childbirth.
Maternity Glenda can give birth to 2 males, 1 male and 1 female, 1 female and 1 male, or 2 females.
Each of these possible outcomes is a simple event. A simple event is an event that has only one possible outcome. As we know, the probability of a simple event is 1 divided by the total number of simple events. We've got 4 possible events, so the probability for each of these simple events occurring is 1/4.
Let's go over the events one more time. In event 1, the first baby is male and the second baby is male. In event 2, the first baby is male and the second baby is female. In event 3, the first baby is female and the second baby is male. And in event 4, the first baby is female and the second baby is female.
Since events 2 and 3 produce the same outcome, we can combine their probabilities, giving us a probability histogram that looks like this. Remember, X represents the number of girl babies maternity Glenda gives birth to.
The probability of X equaling 0, which means Glenda gives birth to 0 female babies, is 1/4, or 0.25. The probability of X equaling 1, if Glenda were to have 1 female baby, is 1/2, or 0.5. And the probability of X equaling 2 is 1/4, or 0.25. This histogram is the probability distribution for our example.
We just used a probability histogram to organize our data. Now we can calculate things like mean, deviation, variance, and standard deviation to help us interpret these results.
When making a probability distribution, we can still calculate the mean, only we give it a different name. In a probability distribution, the mean is known as the expected value. Out of all the possible values for little x, the expected value is the value for little x that should end up being the average in the long run. We use mu to represent it, but you might also see it depicted as e of x, so don't be surprised if the symbol for the mean looks a little different than before. Here's how to find it.
You may recognize the big italic U-looking thing on the left as the Greek symbol mu. Mu is also used to represent the mean of a population. Here, we'll use it to represent the expected value of x. The expected value of x can also be written as e of x, but don't worry about that, just think of it as mu.
To find the expected value of a probability distribution, multiply each possible value for x by the probability of x occurring, and add all those values together.
How did that big E get in there?
That big E-looking thing is not an E at all. It's actually the Greek letter sigma, and it stands for sum. It's just a reminder that once you've multiplied all the x values and their probabilities, you need to add them all together.
Using the data from our maternity Glenda example, the potential values for little x are the possible number of female babies she can give birth to. Again, she can give birth to 0, 1, or 2 female babies.
The probability of 0 female babies is 1/4. Multiply 0 by 1/4 and you get 0. The probability of 1 female baby is 1/2. Multiply 1 by 1/2 and you get 1/2. And the probability of 2 female babies is 1/4. Multiply 2 by 1/4 and you get 1/2. Total up 0, 1/2, and 1/2, and we see that the mean or expected value for x is 1. So we can say that it's most likely that x will equal 1, and maternity Glenda will bring 1 female baby into the world.
We found our mean, but what would the mean for a probability distribution be without its old friends, variance, and standard deviation? Let's start by calculating the variance.
Take the deviation, the value of x minus the mean, and square it. Do this for every possible value of x. Add those values together and divide by n, the number of values for x.
That's how we find variance for a population. But to find the variance for a probability distribution, we use a slightly different formula.
For a probability distribution, the variance is represented as lowercase sigma squared, just like it was when we found variance for a population. We're still finding the deviations for the different x values and squaring them. Only this time, we multiply those by the probability for the x value we just squared.
Got that? Each value of x has a deviation. To find the variance of a probability distribution, we need to find the deviations for the different values of x. To do this, subtract mu, the expected value of x, from x. Once you've found the deviation for an x value, square it and multiply by the probability of that x value occurring.
Once you've done that for each value of x, sigma kicks in and we add everything up.
Yeah!
And that's the variance for your probability distribution.
This formula may look intimidating, but the process for finding variance is more or less the same. Let's take a look using maternity Glenda.
Here's the probability values we found for our maternity Glenda example. The probability of x equaling 0 is 1/4. The probability of x equaling 1 is 1/2. And the probability of x equaling 2 is 1/4.
To find the variance, first thing we want to do is plug in our values for x, 0, 1, and 2. The corresponding probabilities, 1/4, 1/2, and 1/4, and the mean, 1. Now subtract the mean, 1, from each x value to find the deviation. We get -1, 0, and 1. Take each deviation, square it, and we get 1, 0, and 1. Next, multiply those deviations by the probability of that x value occurring. So we multiply 1 by 1/4, 0 by 1/2, and 1 by 1/4, and we get 1/4, 0, and 1/4. Add them all up, and we get the variance, which in this example comes out to 1/2.
The variance gives us a general idea of how much our figures are spread out around the average. The variance doesn't mean a whole lot on its own, but it comes in real handy when we find the standard deviation, which we'll do in a second. So remember that the variance is just the means to an end.
Now that we've found the variance, let's try out that formula for standard deviation. For random variables, discrete and continuous, we use the same method as we did to find the standard deviation of a population. The standard deviation for a random variable, designated by the lowercase sigma, is simply the square root of the variance.
The variance for the maternity Glenda example is 1/2. Once we have the variance, finding the standard deviation is pretty easy. All you need to do is take the square root of the variance. We take the square root of 1/2, and we get roughly 0.707, which is the standard deviation for maternity Glenda.
Don't forget, the standard deviation is a unit of measurement, like a foot or a nautical mile. It tells us where measurements in the data set lie in relation to the mean. In general, most measurements should fall within 1 or 2 standard deviations from the mean.
With both the variance and standard deviation, we've graduated a bit in difficulty and jargon, but the meaning is exactly the same.
Let's go over the results of our experiment again. To predict the sex of the twins, we used the number of female babies as our value for x. We found the expected value, or the mean, represented by mu, to be 1. The variance is 1/2, and the standard deviation is 0.707. So since our expected value is 1, it's most likely that maternity Glenda will have 1 girl and 1 boy.
What we just saw was a stripped-down bargain basement version of a probability distribution. Hopefully you've got the basics down, and now we can start to build an understanding of probability distributions.
Throughout the high-stakes world of statistics, we use several probability distribution models. Just so you understand the applicability of these models in other fields, a great deal of what we'll cover in the remainder of the video is used frequently in physical science, social science,